Okay, hey everybody. So the plan for today is to discuss Green's theorem, section 16.4. Now, before we get into Green's theorem, I want to clarify um, a little point here. We need to understand this notion of a simple, positively oriented closed curve. So we want a curve that basically looks like this. Okay, so to make this precise, what do we mean? Well, we say that a curve is closed if its initial and terminal points are the same. That is, if we have a curve parameterized by r of t going between a and b. So if r of a equals r of b, so we have our initial point r of a, and that's equal to our terminal point r of b. So we start and end at the same point. That gives us a closed curve. We say that our closed curve is simple if it's non-intersecting. So we don't want a curve like this that intersects itself. We want a non-intersecting curve. And if we want to be more precise about what we mean by a non-intersecting curve, we say that again, if we have our curve parameterized by r of t going between a and b, this is simple if given x and y in closed AB with x less than y, r of x equals r of y implies that x equals a and y equals b. In other words, the only time that our curve in some sense intersects itself is at those two endpoints where the curve comes back together. So it never really truly intersects itself. And we say that a simple closed curve C, so like the one I've drawn down here, in the plane is positively oriented. We have to decide which way we're going to go around C for this discussion. So we're going to suppose that we're going around C in the positively oriented direction, which we can define a few different ways. We can define, as we're looking at it here, traversed counterclockwise. I think for most people, that's, pretty straightforward. We can also talk about when kind of walking around the curve, so to speak, if we were physically imagine ourselves standing on this curve and walking in the direction of the arrow, the enclosed region, maybe we call it D here, the finite region, this closed curve splits the two-dimensional plane into two regions, an infinite region on the outside and a finite region on the inside. This finite region is to our left. Why did we pick counterclockwise and to the left? Well, just because we have to pick a direction, and that's the convention. There's nothing inherently better or worse about going this direction versus another one, the other way, but we have to pick a direction. This is the way we choose as the quote positively oriented direction. Or another way we can think of it, this might have a bit more of like a physics kind of feel to it, is that it follows something like a right-hand rule, something like that. That is, if we take our fingers on our right hand and kind of curl them in the direction that the curve is going, and we stick out our thumb kind of points toward us. Where if it was oriented the other way and we took our fingers of our right hand and curled them that way, it's kind of hard to do. You have to kind of flip your hand around, but then our thumb would point away from us, right? If it was oriented the other way, we might say that follows something like a left-hand rule where our left hand, when the fingers curl around, our thumb would point toward us. So we might say it follows something like a right-hand rule. So any of these ways we can think about it. I think the easiest way to think about it is it's oriented counterclockwise. Is probably the most straightforward. And then a little bit of notation. Often if we have a simple closed curve that encloses a finite region we call D, we often call this curve the boundary of D, and we write it with like a partial notation, partial derivative notation, a little curly d of D. So this curve might be also called the boundary of D. You might see that notation floating around as well. Okay, so after these definitions, we can state Green's theorem. So let's let C be a positively oriented, piecewise smooth, simple closed curve in the plane and let D be the region bounded by C. So basically, like our picture up here, if P and Q have continuous first partials on an open region that contains D, then we can say the following. We can say that the line integral over the curve C of f dot dr, which we could alternatively write this way if we chose to. That's just a different notation for the same thing. The real meat of the theorem is here, that instead of doing this line integral over this curve, we could do a standard double integral of some integrand dA. And the integrand that we will integrate is partial of q with respect to x minus partial of p with respect to y. So here q is the y component of f, and p is the x component of f. So this is what Green's theorem says. It says that instead of doing this line integral, we can choose to do a double integral. Now, maybe in some situations doing the line integral is easy and we'd rather do that than the double integral, but maybe in other situations it's easier to use Green's theorem and switch to a double integral and perform the double integral instead of the line integral. So this gives us just another method of attack for a certain problem. And it also gives us, we'll see, a little bit of extra mathematics that we can use and bring to bear on particularly one topic that we kind of skipped over some of the details on in a previous section. Okay, let's go through a sketch of the proof of Green's theorem. So let's assume that our curve is what I'm going to call kind of x simple and y simple. What do I mean by that? Well, what I mean is I have a plane x and y, and I will define a region as, say, x simple or y simple if, oh, let me redraw this curve. I'll draw it a little bit better. I'll just draw it smoother like this. If it's true that I can break this area, let's say I'm going from, say, x equals a to x equals b, and I can break this into a bottom curve. Let's call it y equals y1 of x, and a top curve y equals y2 of x. So I see that the enclosed region, which I may call D, it can be written fairly simply because y just goes from y1 up to y2. You could imagine if I had a curve that, did something like this. Well, this is going to be very difficult for me to say what are my upper and lower bounds with respect to y, right? Sometimes I'll have to have several upper and lower bound kind of different regions and so on. So this would not be an x simple or y simple closed curve. So we want this ability to kind of slice the curve into a top part and a bottom part and have just one top part and one bottom part. And we also want the ability to do that the other way as well. If I take y going from, say, C to D, and then I want there to be a left part and a right part that are kind of unambiguous. Okay, so if I do have this, then I can say, well, if my curve is positively oriented, if it's oriented in the counterclockwise direction, it should be being traversed in the direction I've indicated here. Then let me take a look at one part of this integral, namely the integral of p dx. I'm going to leave integral of q dy alone for right now. I'm just looking at integral of p dx. Now let me say that this green curve on the bottom here, I'm going to give it a name, C1, and this red curve on the top here, the name C2. So I see that the integral over the curve C, the whole loop of p dx, is integral of C1 p dx plus integral over C2 p dx. Now, integral over C1, I see that that's the, what? That's the integral as x goes from A to B. So we're being really careful with our direction here. X going from A up to B of P dx. But P is, when we're on this green curve, P is a function of x and y, but y is restricted to be y1 of x. So it's x comma y1 of x dx. Right, on the green curve, the bottom curve, well, that's where y is always y1 of x. So if I am given an x, that also determines my y value, y1 of x. Okay, so that's the bottom part of the curve. That's the green part of the curve. Plus, I need to add on the top part of the curve. This is the integral. Now here I'm going from right to left. So this is x equals from B to A of what? P of x comma y2 of x dx. Same idea as the first integral. But I can wrap these under the same integral now. Integral x equals a to b. And here I kind of want a y2 of x minus y1 of x because the y2 is like the top curve and y1 the bottom curve. So I'm going to put a minus out in front. P of x comma y2 minus p of x comma y1. Now here I might look at this and realize that this is kind of like just p of x comma y being evaluated from y equals y1 of x up to y equals y2 of x. Right? This would just be evaluating p of xy with y going from y1 to y2 dx. But this looks awfully a lot, just this inside piece, just this integrand, it looks awfully a lot like the result of an integral maybe coming out of the fundamental theorem of calculus, just a function evaluated at two endpoints. And in fact, it kind of seems like this might be, say, the integral of, well, the integral of something dy, so the integral of the partial of p with respect to y, dy, and then, of course, a dx here at the end, where y goes from y1 of x to y2 of x. But wait, if I have x going from a to b, and y going from y1 of x to y2 of x, that's just a description of this region inside of the curve D. In other words, this is just the double integral over D of something. Well, what would that thing be? It will be negative partial of p with respect to y dA. This is simply a double integral. So in summary, what do I have? I have integral over c of p dx equals the double integral over d of negative partial of p with respect to y dA. Completely analogously, when I say something is analogous, that's maybe kind of a keyword to maybe as an exercise, try to work out the details. It's very similar to this process I just did here, but pull out a blank sheet of paper, see if you can go through the details and make this work out. But analogously, integral over c of q dy equals the double integral over d of the positive partial of q with respect to x dA. And then, of course, adding the two, integral p dx plus q dy, I end up adding these two double integrals. I get the double integral over d dA of partial of q with respect to x minus partial of p with respect to y. And that is Green's theorem. So it's a sketch of the proof, but it's a pretty enlightening sketch, I think. Okay, so a couple notes, a couple questions about Green's theorem. Well, the first note is one thing that really stands out with Green's theorem is we're used to seeing symmetry between x and y in a lot of our theorems, right? Like, why should I fundamentally get a different result if I swap the roles of x and y? I mean, aren't I in some sense just like finding an area or something like that? Shouldn't that be the same if I swap x and y? Why do I have, dq dx has to come first and then minus dp dy? If I switch the two, I'm off by a negative sign. What happens here? Why isn't Green's theorem symmetric? Green's theorem isn't symmetric because if I exchange the roles of x and y, let me see if I guess I can use black here. If I exchange the roles of x and y, effectively what I'm doing is I'm flipping everything about this line y equals x. But if I take a positively oriented curve, remember we had to choose a way to traverse the curve, either counterclockwise or clockwise. We chose counterclockwise. If I flip that over, then it orients the other way. If I exchange the roles of x and y, I traverse my curve in the opposite direction, and we know that that's going to pop out a negative from our line integral. So why is it? It's because we chose the positively oriented direction. It's because we chose to traverse the curve this way. So dq dx has to come first and then minus dp dy. If I had chosen instead to traverse it the other direction, I could flip the two, dp dy minus dq dx. So this choice of which way we traverse the curve is what leads to this kind of breaking of the symmetry. Okay, note 2, and this is maybe a seemingly more important blow to the proof is, well, I mean, okay, we dealt with these kind of x simple and y simple, so to speak, curves, but I mean, this really seems like a special case. I mean, even if I draw a fairly simple curve like this, it's immediately not as simple. It doesn't fall under this category. So am I only dealing with like circles and ellipses here, or can I generalize this proof? Well, we can generalize the proof, and in fact, the idea of the generalization of the proof, this underlying idea, is actually very important as well from a practical standpoint. So let's consider a curve like this. Well, I could construct this curve in a different way. I could construct the curve by taking, say, the top piece and going, say, across like this, and then taking the bottom piece and coming across this way. Now, these two straight line segments in the middle, the two that I kind of added in here, these are really the same line segment. I'm just drawing them a little bit separated, but these two bits here, this is the same line segment, so they should be glued on top of one another. But just to illustrate, I'm drawing them separately. But I noticed that these curves really are equal in a sense because this bottom curve here is traversed moving to the left, and the top curve here is traversed moving to the right, so they end up canceling out. Because the directions are opposite, the contribution to any line integral is, one is the negative of the other, and then we add them all up and those pieces cancel out. So the point is that I can kind of add in, let me do it in a different color, I can kind of add in a slice, and I can see that the line integral over C is like the line integral over the top part of C, and then across in the direction left to right along that blue middle line. And then plus the integral the bottom part of C, then right to left across the blue line. Again, the left to right and the right to left across the blue line cancels that blue line's effect out. So I end up with just the same result as the integral over C, but I can split my region up like this. So what if I have some funky region like this, some funky curve like this? Well, what I can imagine doing with Green's theorem is I can imagine splitting this up into a whole bunch of really small rectangles. And in fact, if I split this into an absolute ton of rectangles, I'll end up with essentially one of two cases. Either a case like this here, where I have an actual rectangle, which is, of course, x and y simple. The top and bottom curves, the left and right curves are trivially easy. Or I'll end up with something that's like three sides of a rectangle and then one curvy side. So of course, again, this is an x simple and y simple region. So I can imagine doing this proof over each one of these rectangles, or kind of like three-sided rectangles with one curvy side. That the proof will apply to each of these segments, each of these little chunks of region, or whatever you want to call them. And then, of course, when I glue everything together, all of the blue lines will all cancel out, because we're going to traverse each little segment of blue line wherever it is. Say maybe this one here, we're going to traverse it once going bottom to top and once going top to bottom for the left versus right box that it's a border of. And then its effect is going to cancel out. So all of these internal blue lines cancel out, leaving me with just the effect of the black outer curve C. But my proof over the x and y simple regions will hold on each of these boxes, provided I use enough boxes and chop them up small enough. But this idea is actually a pretty important idea, that we can chop regions into maybe more convenient regions. In some cases, that's very helpful, and that our kind of contributions of the chopping parts, the lines we get by chopping, they just end up canceling out. Okay, so a third note. There's this really nice general idea. When we're going through, especially these vector calc sections, it can really seem like we're just doing a bunch of random stuff, and each topic is just completely different from the previous topic and nothing really ties together. So I want to give a little bit of a preview here. We won't know exactly what this stuff means right now. And I want to look back a little bit as well and maybe tie everything together. So really everything from the fundamental theorem of line integrals to Green's theorem to the upcoming theorems, Stokes' theorem and divergence theorem, these are all essentially generalizations of the fundamental theorem of calculus part 2. So what does the fundamental theorem of calc say? It says that the integral a to b of, well, a function But if the function is a derivative, f prime of x dx, this is f of b minus f of a. So if I add up a bunch of local property, the derivative is a local property, right? We have the derivative function at a point. If I have a whole bunch of local property that I kind of integrate over, that I kind of add up or accumulate together, I end up with just an evaluation at the boundary of an interval is just the endpoints. So I accumulate a local property, and that's equivalent to an evaluation of something related to that local property at the boundary. Or I accumulate a derivative, and that's equivalent to an evaluation of the antiderivative at the boundary. What does the fundamental theorem of line integrals say? It says that I accumulate, I integrate. Here we use a line integral, but I integrate grad f, I integrate a derivative, and that gives me an evaluation at the boundary. I integrate over some line between 2 points. That integral is equivalent to evaluating the function at the 2 endpoints. What does Green's theorem say? It says if I integrate something looks like a derivative, dq dx minus dp dy, we'll actually see that this is even more closely tied to the idea of derivative than we might even realize now. We'll see that in the next section or two. So this is related to something called the curl of f, which is a type of derivative. Well, if I integrate this derivative over an area, I'm doing a double integral, that's like an evaluation over the boundary. Well, here we have a boundary of a two-dimensional region, so that boundary is a one-dimensional curve. I need to somehow evaluate over that one-dimensional curve, and that becomes a single integral from our double integral. So I accumulate over the boundary, and that's equivalent to taking the double integral of something that's like a derivative. Stokes' theorem says something fairly similar. It says that there's some notion of, quote, derivative. Again, this idea of curl, but there's some notion of derivative over a surface. If I accumulate that, if I take the double integral over that surface of that, quote, derivative, that's like evaluating over the boundary of that surface. And the divergence theorem says actually something similar as well. If we take a triple integral of a derivative of f, in this case, it's what we call the divergence of f. That's another type of derivative of f. If I take the triple integral of that, quote, derivative, that's equivalent to a double integral. The boundary of a three-dimensional volume is a two-dimensional surface. So this is the integral over the boundary of a three-dimensional volume. It's an integral over a surface of the function. I accumulate the value of the function over a surface instead of accumulating the value of the derivative over a volume. So integrating a local phenomenon over a region is equivalent to evaluating the antiderivative over the boundary of the region over one smaller dimension related to that region. So this is kind of a unifying concept between, I suppose, really all of calculus, but certainly these three theorems that are sometimes called the fundamental theorems of vector analysis or vector calculus. So Green, Stokes, and the divergence theorem are all kind of like fundamental theorem of calculus generalized to vector calc. And they're just kind of different perspectives on a similar idea. So that's a unifying principle between these. It can seem like these are all just disjointed, strange things that come up, but they all really are saying, in some sense, the same thing, but just through slightly different lenses. They're all saying if we integrate a derivative over a region, that's like evaluating the function over the boundary of that region. Okay, so let's look at a couple of practical examples. All right, so example one, we want to compute the line integral of f dot dr, where f of xy is sine x, comma, x squared y cubed, and c is the curve consisting of straight lines. Let's draw this. Starting in 0, 0, going to 2, 0, going to 2, 2, and then going back to 0, 0. Now, I suppose we could do this line integral. We could make three parameterizations for the three pieces of the curve. We could do three different line integrals. We could do that. It wouldn't be bad practice to do that to make sure you get the same answer. But I look at this and I say, well, this region enclosed by these, by this curve, by these three pieces of the curve, is actually a pretty darn simple region. It's just a triangle. So if I look at this region D enclosed in here, I do note that my curve is positively oriented. It's an important note. If it wasn't positively oriented, I could just hit it with a negative sign and maybe make it positively oriented. But okay, I have a positively oriented curve enclosing a region D. Well, Green's theorem says that the integral of f dot dr, where f is p comma q, is the double integral over the enclosed region D of dq dx minus dp dy dA. But this double integral isn't hard to do at all, or it's not hard to set up the region, I should say, at all. X just goes from, say, 0 to 2, and y goes from 0 to, well, this is the line, just y equals x, going from 0, 0 to 2, 2. And my integrand turns out to not be that bad. dq dx is 2xy cubed, and then minus dp dy, but there are no y's in p, so that's just 0. So this bit is 0. And then dy dx. And we do our inner integral. We integrate dy. We get x y to the fourth over 2 from 0 to x. And this gives me x to the fifth over 2. Integrate that dx. This gives me x to the sixth over 12 from 0 to 2. Or that's 2 to the sixth over 12. And we can do a little bit of simplification there and get 16 over 3, 2 to the fourth over 3. I think this was much nicer than trying to put together three different line integrals with three different parameterizations and evaluate all of those. But again, if you want some practice on line integrals, you can go and do that. It wouldn't be that terrible. These aren't too terrible parameterizations to do, and check that you get the same answer. Okay, let's take a look at example 2 here. So let's take a look back at this. Field that we saw before, where it kind of had this strange property that I didn't write it down there, but it had the strange property that here's P and here's Q, that dP dy equals dq dx. So that makes us say, oh yeah, this is a conservative vector field, but the integral over a circle of radius r centered at the region actually gives us 2 pi. We usually think of conservative vector fields, well, we kind of always think of conservative vector fields over a closed loop, when integrated over a closed loop, is giving us 0. What happened here? Well, really what happened here was that, of course, dp dy and dq dx and p and q themselves are not defined at the origin. So really this is true for x comma y not equal to 0, 0. And because this circle centered at the origin does enclose the origin, this kind of blows up, right? This idea of conservative field, it doesn't help us with this line integral here. And if we do the line integral, we end up with getting 2 pi. What we would like to do is actually to prove that the integral over C, some closed curve, some simple closed curve, of f dot dr equals 2 pi, where C is any simple closed curve that contains the origin in its interior. So if I have the origin here, this one point where this field and its partials kind of blow up, I know that integrating over CR gives me 2 pi. But I want to make the argument that if I have any curve that encloses the origin here, that line integral will be 2 pi. Okay, well, I obviously need to leverage this idea of the integral around a circle somehow. What I can do is I can look at my curve here. I'm going to try to recreate it. I can look at my curve here and I can look at just the top half. So the top half is going this direction. And then I can think I have a line segment kind of coming in along the x-axis. I'm drawing it a little bit above the x-axis so we can see it. And then going around the top of CR and then coming over this way. So this line segment is going that way. And so maybe I'll just leave that as it is right now. And then for the bottom part of C, I see that I would kind of come down like this, over like that. But now again, when I get to the x-axis, I can make my way in towards CR, around CR, the circle of radius R, and over here, whoops, one that's trying to help out a little too much. There we go. This is oriented this way, this way, this way, and this way. I noticed that, and again, these horizontal segments are right on the x-axis. I've drawn them split apart so that we can see that they're two different segments, but they'd be right over top of one another. So I can see that this bit here and this bit here completely cancel out. So what I end up with is something that looks like the curve C, which I'm probably going to get more and more lazy at drawing, but that's the same curve C is up here and as the kind of outermost curve of this picture on the bottom left. And then I have this inside, I'll just draw it all in green this time, CR. Note that CR is traversed the opposite way from C. And I see what I've done here is between C and CR, I've created a region, which I'll call D. I also see that 0, 0 is not an element of D. Now, one, I guess, minor side note that I kind of glossed over is, how do I know that I can fit CR inside of C? Well, remember that CR is a circle of radius R, where radius R is arbitrary. We're also assuming that C is a simple closed curve that contains the origin in its interior. In other words, there exists some open set, some open ball around the origin that's fully inside of C. So if the origin was allowed to, say, be right on C, right at the boundary, I might not be able to make an argument like this, but here the origin is comfortably inside of C. I might have to find a really small radius so that the point of C that's closest to the origin, maybe it's really close and I have to pick a really small circle around 0, 0, but I can always pick such a circle. But by picking this circle, I've kind of excised 0, 0 out of my region inside of my quote, inside of my curve C, or of the inside of this domain D. Okay, now what can I say down here? Well, I can say that integral over C of f dot dr minus the integral over CR f dot dr. Well, again, I've kind of just used a little kind of top curve here. That's some curve whose interior region does not contain the origin. And I've also used some bottom curve here, again, whose interior region doesn't contain the origin. I've just kind of glued them together. I can apply Green's theorem here. So this ends up being the double integral over D of the partial of Q with respect to X minus the partial of P with respect to Y dA. And again, importantly, 0, 0 is not in D. But remember that partial of P with respect to Y equals partial of Q with respect to X, except at the origin. But if we're not considering the origin, these partials are equal. In other words, this partial is equal to that partial. When I subtract them, I'm just integrating 0 over this domain. That's just 0. Or in other words, integral over C of f dot dr for an arbitrary curve C enclosing the origin equals integral over CR, and I suppose I could put circles like that, f dot dr, but that's just 2 pi. This trick is actually one that is a crucial one in complex analysis, and something, more complicated than we're doing here. This has applications to things like the residue theorem, and I think it's Cauchy's integral theorem, and a lot of different ideas like that, where you're taking some regions, chopping them up into, in some sense, like boring parts and interesting parts. And what we've done here is we've just basically thrown out the boring part that doesn't contain the origin. And we said the origin is really the only point of interest, in a sense, here, that gives us any output that's non-zero. It's what's giving us this output 2 pi, where kind of things blow up. That's what gives us the interesting part of the output. And everything else other than the origin, it just has a 0 contribution, so we don't really care too much about it. And in fact, we could shrink this circle down quite small, and we could really argue that it's really only just the origin that gives us something interesting, something non-zero here. Okay. So lastly, I want to revisit an idea from last section. We talked about conservative vector fields. And we had a partial derivatives test where we said that we made this claim that f equals pxi plus p of xyi plus q of xyj. That's a conservative vector field if and only if dp dy equals dq dx on some domain of interest. We made this claim. We didn't really prove it. We gave kind of a hand-wavy argument for one direction, but didn't really prove the other direction. Let's go through and prove this now. And we'll see that we'll use Green's theorem to prove an important part of this. Okay, so first, just to remind us of some details. Definition, F is a conservative vector field on D. The definition of that is that there exists little f such that big F equals grad little f on D. In other words, big F is a conservative vector field means that F is the gradient field of some potential function little f. Okay, we have two lemmas. A lemma is kind of like a small proof that's going to help us with the bigger proof. So lemma 1, and these are both in the book, and we've discussed both of these before, but just a quick reminder. Big F is independent of path in a region D, if and only if the integral over a closed curve C, f dot dr equals 0 for all closed curves in that region. Okay, so this is kind of a geometric proof. We consider a closed curve C, and we consider 2 points, let's call them A and B on C. And I note that I can break C into kind of a C1 here. Let's say that C is positively oriented. That's going that way. And a C2 over here. So I have that C equals C1 plus C2. Okay, so I can, let me give myself a little more room here. I can prove the kind of this direction that if f is independent of path, then the integral will be 0. So f independent of path implies that integral C1 f dot dr. C1 takes me from point A to point B. Well, this has to be equal to the integral of, well, not quite C2, but negative C2. We'll call negative C2. That's the path C2, but traversed in the opposite direction. If f is independent of path, then if I take two different paths between A and B, I need to get the same result. That's the definition of independent of path. But integral of negative C2 FDR is just negative integral C2 f dot dr. If we traverse the path the opposite direction, we just get the negative value of the integral. Well, but wait. Integral of C f dot dr is just integral C1 f dot dr plus integral C2 f dot dr. Here C2 doesn't have a negative when I put it in here. But integral of C1 plus integral of integral over C2 equals 0. So if f is independent of path, then the integral around a closed curve is 0. We have to prove the other direction as well, that if the integral around any closed curve is 0, then f is independent of path. So here we have that 0 equals integral over the closed curve f dot dr. Well, I mean, the proof is very similar to before. That's like integral over C1 f dot dr minus integral over C2 f dot dr. Well, but that says that integral over C1 minus integral over C2 equals 0. Says that integral over C1 f dot dr equals integral over C2 f dot dr. So the closed integral being 0 says that whether I take path C1 or C2, I get the same answer. Okay, so we've proved lemma 1 up here. Oops, and I missed a negative here, didn't I? So C is C1 plus C2 or C1 minus integral over negative C2. So that they're going in the same direction. So pop that negative on the C2s in this second part here. Okay, we also have lemma 2. F is a conservative vector field on D if the line integral is independent of path. So if we have path independence, then we have a conservative vector field. And I'll just refer you to the book for the proof of this lemma. Okay, so now let's try to prove our claim. So again, what was our original claim? That we have two things that are equivalent. The first is F equals Pi plus Qj is a conservative vector field. And the second is that dp dy equals dq dx. So let's prove A implies B, and then we'll prove B implies A. So if F is conservative, then F equals grad little f for some little f. But that says, well, big F is P comma Q, and grad little f is Fx comma Fy. So this says that P equals Fx and Q equals little Fy. So then what is Py? That's Fxy. And what is Qx? That's Fyx. And provided that we have nice continuous partials and so on, these are equal to one another. So if F is conservative, then dp dy equals dq dx. That's the part that we saw easily before. But note that that's actually not the most helpful direction, right? What we want to do is to be able to use this theorem to check and say, okay, because I observe that dp dy equals dq dx, then I know that F is conservative, and then it makes sense for me to go searching for a potential function. That's actually the way that we use this theorem, but we haven't proved that all-important direction yet. Let's prove that now. So let's assume if px equals, py equals qx, then what do we have? Well, then Green's theorem comes into play and says that the integral over a closed curve, f dot dr, remember that's the integral of p dx plus q dy. Well, this is the double integral over the enclosed region D of qx minus py dA. But wait, py equals qx. My integrand is just 0 everywhere. I just have 0 times some area. That's just 0. But what does this say? This says that the integral over any closed curve, f dot dr is 0. That implies f is independent of path. And then we have a lemma that says, if f is independent of path, then f is conservative. So this implies f is conservative, implies that f equals grad little f for some little f, that there exists a potential function, and that big F is the gradient field for that potential function. So this is really the direction of this theorem that we really needed and that we used the most. And it was directly reliant on Green's theorem for this all-important step here. And then also some of our other definitions and lemmas to kind of drive things home. But really, this was the key step, getting this qx minus py integrand that we can see is 0 from our assumption. Okay, so that wraps up our discussion of Green's theorem, and hopefully gives you a little bit of a preview into the next few topics that we'll be covering. And maybe when we go through those, it'll feel like there's a little more rhyme and reason to why we're covering Green's, Stokes, and divergence theorem and how they all kind of interrelate to one another.